Okay, so this introduces the unbalanced delta for the module. So I'm just going to go over some worked examples, one using a purely resistive circuit, so no inductors or capacitors there, and we'll move on to an RLC circuit. So here we have our circuit. We have delta connected with 3 resistors, one 10 ohms, one 7.5, one 12, and we have 9 volts between 2 of the lines here. So this is the line voltage. And we're asked to fill in this table. So we're asked for our line and phase voltage, our impedances, our lines and phase currents. So first of all, what is the line and phase voltage? Well, the line voltage is the voltage between the brown and the black, so this would be the line 1 voltage. And the phase voltage is the voltage drop across the resistor, the phase voltage. And as we can see here, the nodes that the voltages are connected to is exactly the same as the difference between the 2 lines here. So the line voltage is the phase voltage. So when we calculate phase 1, we can just take our line voltage, which was given as 9 volts, take that as our reference at 0 degrees. And we can just add that to our table there. So when we go for our next line voltage, we're taking the line, the voltage difference between the grey and the black, or the black and the grey line. And the phase voltage is just exactly the same as you would expect. We've got the nodes here connected. The phase drop, the voltage drop across this resistor is the line voltage. So when calculating this, hopefully this should be a bit easier for you to remember now. We have our phase shifts. So the line voltage, line 2 voltage is negative 120 degrees, and the line 3 voltage is positive 120 degrees from line 1, taking that as our reference. So this should be pretty straightforward to calculate. Phase 2 voltage is 9 volts minus 120, and phase 3 is 9 volts at positive 120. Again, we'll just fill that in and we'll add our impedance values as well. So we're taking impedance 1, the phase 1 impedance, 10 ohms, phase 2 and phase 3, 12 and 7.5 there. And we've added our line and phase voltages here. So what happens when the line current comes to this node here? So just say this is a parameter that we can calculate, but what happens to the current using Kirchhoff's current law? What would you expect to happen here? Well, on the positive cycle, we'll have part of the current passing through this branch here, and we'll have part of it passing through this branch here. So what about this? What about the current on the black line? Again, it reaches this node here, and it'll split into 2. So part going through the 10 ohm resistor and part going through the 12 ohm resistor. And finally, what would happen to the grey line current? Well, it's going to travel on the positive part of its cycle, come to this node here, and yep, you guessed it, part is going to split through to the 12 ohm resistor and part is going to go through the 7.5. So the difference between part of the current that splits from the brown line and part of the current that splits from the black line and passes through this resistor here, this is the phase current, and we denote this by I, brown, black. So this is the difference, the phasor difference between the portion of the current that comes from the brown line and portion of the current that comes from the black line. So this is our phase 1 current. Our phase 2 current, by the same method, well, we're going to take part of this grey line and part of this brown line. This is actually phase 3, sorry. And phase 2 is the black line and the grey line. So the black current that splits through the 12 ohm resistor, and the part of the current that coming from the grey line that passes through the 12 ohm resistor. So we have our phase currents here. So phase 1, phase 2, and phase 3 here. So on the negative part of the cycle, what would you expect to be the line current? So say the current is travelling in this direction here, and it's reaching this node. So what will the expression be for this? Well, we're going to have this current travelling up this direction, and we're going to have this current travelling up this direction, meeting at this node. And it's going to be the phasor difference between those two. So we got the phase 1 current here minus the phase 3 current. So what about this one? What do you expect the current here to be? Well, it's coming from this node, and which phase currents are attached to this node? Well, we got phase 2 and phase 1. So it will be the phasor difference between phase 2 current and phase 1 current. And if you're already a couple of steps ahead, you'll have figured out that the line 3 current is the difference between the phase 3 current and phase 2 current, as they are both reaching this node here. So this is just an illustration to show you, if we take just a purely resistive circuit and a balanced circuit as well. So the impedance is the same, so the currents here are exactly the same. And just for an illustration, we have phase 3 current here, which is a combination of the phasor of the black and the grey phases. And we've got phase 1, which is a combination of the brown and the black line current. And we have line 1 current. So each point along the time axis here, we're going to subtract phase 3 from phase 1. So here at point 0, we should have line current. It should be equal to the negative of the phase 3 current, because phase 1 current is at 0. How about this portion here when they both intersect? Well, they're both equal, and they'll subtract to 0, and this is why we've got 0 here. So you can do this for every instant in time along the time axis here. You subtract phase 3 current from phase 1 current, and you plot those, and what you get is this nice sine wave. Now, if it was perfectly balanced, when we were dealing with balance, we had a nice easy equation to deal with to convert the phase current to the line current, which was √3 times the magnitude with a phase shift of minus 30 degrees. However, it's not so simple, because we don't have equal impedances along the lines. So we have to have a means of calculating this. We have to do this longhand. We can't take the shortcut here. So given that we have our phase voltages and our line voltages as they're equal, and we have the impedances, we should be able to now calculate the phase currents and the line current. So let's calculate the phase currents. Well, phase 1 is equal to the voltage across phase 1 divided by that impedance. And that would be 0.9 at 0 degrees amps. And we can add that to our table here. Now notice these here are our phase currents, and these are our line currents. So I'll make sure you denote it right with the subscripts. Okay, so we can calculate phase 2. Well, we've got the current of phase 2, and that is the voltage of phase 2 divided by the impedance of phase 2. And that comes to 0.75 at minus 120 amps. And we can just add it to our table there. So phase 3, the same process. Again, it's just a process. If you know how to do it once, you should be able to do this for other phases as well. Again, be careful. Here we're using phase 3 voltage, so this is positive 120 degrees this time. And we get 1.2 at 120 degrees using the Z3 impedance. Alright, so now we have our phase currents, all three of them. We can calculate our line currents. So here is the graph depicting what we're looking for. So we have these here, we have our phase currents, and we're looking for these. So what we have to do is we have to do the subtraction. So line 1 is equal to the current of phase 1 minus the current of phase 3. And what I would recommend is changing that into rectangular form. Now I'm assuming that you're pretty comfortable doing this already. So changing that to rectangular form, it makes it easier to then go ahead and add these. Big warning, you've got a negative and you've got another negative, a double negative. So always make sure you put the brackets here, because what you're doing is you're multiplying this whole term here by -1. If you don't put the brackets in, you're going to change this minus 0.6 to plus 0.6, but this plus J.14 needs to also turn into negative J.14. If you don't put the bracket in, it's not going to do that. And that turns to be 1.5 minus J1.04, and that's it in the polar form. So you do this for all of the line currents. So they're adding it to our table. So it's just a process that you have to do. You have to do the longhand calculation. So line 2 current is the difference between the phase 2 current and the phase 1 current. And that's this here. So phase 2 minus phase 1 is line 2. Again, change it to your rectangular. Don't forget the brackets. And that comes to minus 1.275 minus J0.65 and 1.43 minus 153 degrees. Just add it to our table there. And finally, you've got the line current in line 3, which is the difference between phase 3 and phase 2 currents. Again, you've got your line current here, and this node is where you got phase 3 minus phase 2 current. Do that calculation, turn it into a rectangular, and what you get is 1.7 at 97.59 degrees. And we now have all of our parameters. So what we can do, just to double check that we've calculated all this correctly, we have a sanity check. And this states that the sum of the line currents must be 0. So if you add up all of your line currents, they should equal 0. If they've not, you've gone wrong somewhere. So here in this case, it's more or less 0. Rounding errors bring it to just a very small 2.5 times 10 to the -4. I think I was getting there. So very small rounding error, but more or less 0. So we go to work example 2 with an RLC load now. So we're given a circuit like this, a delta circuit. We're given 415 volts at 50 Hertz. And we're given some impedances. So Z1 is 10 plus J2.5. Z2 15 at 14 degrees ohms, and Z3 we're given a resistor of 16 ohms and a capacitor of 25 microfarads. So we're given the impedances in different formats there. First thing to do is calculate the phase and line voltages. Well, phase 1, we're going to take that as our reference as 415 at 0 degrees. Phase 2 is 415 degrees minus 120. And phase 3, as you should all be saying by now, 415 positive 120. So these are the currents that we're looking for, just like the last example. We're looking for here our phase currents and our line currents. So let's calculate our phase currents again. So phase 1 current is equal to the voltage of phase 1 divided by the impedance of phase 1. Well, the voltage of phase 1, as we had last time, was 415 at 0 degrees, and the impedance, which we were given in rectangular form, we convert that to polar when we're doing the division. So I'm assuming you're okay doing that calculation. And what we get is 41.5 at minus 14.04 degrees amps. So that's has got that one there, that phase 1 current. Calculating phase 2 current now, it's just the same, but we're using the phase 2 voltage divided by the phase 2 impedance. This time we're given the impedance in polar form, so we can just directly do this. If you just, so you know, you divide the magnitudes and subtract the angles, and what you get is 27.67 at minus 134. So that's has got phase 2 there. So now phase 3, just the same method. Phase 3 voltage divided by phase 3 impedance. Now this time we're given the resistor and the capacitor value. So what I've directly done here is I've given it an R plus or R minus JXC. And that bit down there, remember XE is 1 over 2 pi FC. So we've got 2 pi times the frequency times the capacitance value, and it's all over 1. Oh, sorry, 1 all over that. So what we get when you do the calculation and whittle it down, so we get the rectangular form, we've converted it to our polar form, and now we've got 3.24 at minus 157.16, and that's has got phase 3 current. So just to summarise, our phase 1, phase 2 and phase 3 currents, we're going to convert them into rectangular to make the line current calculations a little bit easier for us. So calculating the line currents, well, I've got line 1 current is the phase difference between phase 1 current and phase 3 current. And that comes to 43.24 at negative J8.81. Or in polar, 44.13 at negative 11.51 degrees. So that's has got our line 1 current now. Line 2, it's just the same process. And we get 60.29 at minus 170.62. And that's our line 2 current. Finally, line 3, again, it's the difference between phase 3 and phase 2 currents. We get 25 at 48.24. There we go. Remember the sanity check you do? Well, we're going to do it again. The sum of the line currents must equal 0. This is only for delta, by the way. Here I got just a small rounding error, but don't panic if you get a rounding error. As long as it's more or less close enough to 0, then everything should be fine. Alright, thanks for watching.